Okay, we are live now. And you can go ahead, Miguel.
Okay. So thank you, Isabella. It is what it is. It's 1 minute past 4 p.m. here, 7 and 1 minute past in California. Let's wait a couple of minutes to get started so that everybody can join. Okay, it is more than 3 minutes past. Let's get started. So hello, everybody, and welcome to this new talk at CNM. This is in the framework of the series of talks related to the 75th anniversary of the invention of transistor. And today we have the honor and the pleasure to have Alex Grillo with us. He's a particle physicist who actually went to the dark side of instrumentation and microelectronics. He has been involved in particle physics experiments for many, many years, where he has made very important contributions. In particular, that I know more is in CERN experiments like ATLAS, where he has been the electronics coordinator, and also he has been very high level in management and technical level in the upgrade of the Large Hadron Collider and in the upgrade of the ATLAS experiment. And believe it or not, he's still involved in some work like in guidance and consultation and reviews with the current experiments. But anyway, going back to the early times, in the 80s, after his PhD in particle physics in the University of California, Santa Cruz, he was offered a job at Silicon Valley, where he worked in several startup companies and even he worked at Intel. Therefore, he's a direct witness and a player in these amazing years of the start of Silicon Valley, as we know it now. And sometimes at CERN, he spoke to me about those years, and I always wanted to ask him to give us this talk because I always thought it could be very, very interesting to me and to the people at CNM. So now, thanks to Isabella, we can have this talk. So he can tell us about his experiences in those years and the growing period of the what we call now Silicon Valley. So we can have a hint on how those were those times, how was those people, and how it felt to be part of these times of growing and flourishing. So thank you very much, Alex, for accepting our invitation. And just before letting you talk, let me just say that for questions, people can write them on YouTube, and Isabella and me will try and read them later. And now the floor is yours, Alex. Thank you, and go ahead.
Thank you. Excuse me. Thank you, Miguel. That was a very nice introduction. I appreciate that. So hello, everyone. As Miguel said, I'm talking to you from California. the sun just came up about a half an hour ago here. So, and it looks like it's going to be another nice sunny day. We had rain several days ago. We got our first 2 inches of rain for the start of rainy season, I guess. So I will get on with my talk. First, a short overview of what I intend to talk about. I'll cover my experiences working in Silicon Valley from roughly 1978 through 1990. This certainly did not include the start of Silicon Valley. Shockley Semiconductor Lab had started in 1956 and was already bought out by another company by 1960. But it had spawned other companies, especially Fairchild. And companies like Fairchild, and from which many IC companies spun off, and Hewlett-Packard were well established by 1978 and probably considered not to have great growth potential by that time. But there was still considerable room to grow, especially by new companies. Venture capital funds to start new companies, referred to as startups, were plentiful, and joining the startup with the possibility of significant cash rewards was the expectation of many, many young engineers. That was certainly not my intent when I started grad school, or even when I took my first job there in Silicon Valley. But I found myself swept up in a piece of that action, I would claim by pure accident. So Miguel covered some of my background. I'll mention a few more points. I was a student at UC Santa Cruz, and in this 1978, when my talk starts to cover, I completed the data collection for my PhD thesis in December of that year and returned to California from Fermilab, where I conducted the experiment. And I was still had to analyze the data and write my thesis. I contacted a good friend who had been actually my mentor during the early years of my graduate program. But he had left our group to join Hewlett-Packard before I had left for Fermilab. I suggested when I talked to him that we get together for coffee to catch up. His reply was that would be great, and by the way, would I like a job? That completely surprised me. I wasn't looking for that at all. He and 2 other colleagues had left HP to commercialize the technology they had developed there, something called magnetic bubble memory. They had found an investor in Intel Corporation and created a subsidiary of Intel to design, fabricate, and market a commercial example of this technology. As a typical startup company, they were given a certain amount of money to get a product to market before money might be made available. One of the most necessary components for a startup to acquire is the correct workforce to get the job done successfully and on time. Choosing personnel with the needed expertise was essential, but also personnel with the correct personalities. They needed a group to work together for long hours and to solve not only the identified issues, but new surprise issues that materialized. And that's usually always the case. So why was my friend interested in me, a fresh or not quite a fresh PhD, to join the company? My thesis was rather typical of high energy particle physics experiments, but the team working on my experiment was not at all typical. For reasons I won't go into, the personnel responsible for this experiment was limited to myself, 2 more graduate students, 1 postdoc, 1 research scientist, and 3 faculty. There was also a mechanical engineer and a technician. The only individuals full-time on the project were the 3 graduate students and the postdoc. This meager force would be considered impossible for any particle physics experiment today. Many people told us that it would be impossible even in the mid-1970s. I spent the bulk of my graduate time designing hardware, both mechanical and electronic, building and testing hardware, writing the real-time data acquisition software, and operating data collection shifts with my colleague. My friend knew what hardware and software I was capable of completing, and this new magnetic electronic technology raised issues outside the normal electronic problems encountered by Silicon Valley companies. He also knew that my physics background might offer more creative solutions for some of these problems. For personal reasons, I had already decided not to pursue a normal postdoc position once my thesis was completed. I had made up my mind to find a job in the electronics industry, but since my thesis wasn't completed yet, I wasn't actually looking for a job when I talked to him. I won't go into the details of this magnetic bubble memory technology, but I wanted to give you a short overview of what made it attractive. I just wanted to show you that we weren't crazy working on this new, different technology for many years. To do that, we need to look at what storage technologies were available in the 1970s through the 1990s. Rotating media were large boxes that filled 19-inch racks and were sensitive to vibration and contamination in the air. The floppy disk technology was favored by the microcomputer industry, but capacities ranged from 128 kilobytes to up to 1.5 megabytes. They were also sensitive to vibration and contamination. Electronic memories were either volatile DRAM or non-volatile EEPROM or E²PROM. The E²PROM was very slow to write and was limited to a very few rewrite cycles. You really couldn't use it as a replacement for a disk drive. The solid-state memory devices that we have today required significant technology advances at the end of the time period that I'm talking about. In the 1970s, magnetic core memory which were non-volatile, were still in use, but they were very bulky and expensive, not very attractive to microcomputers. The magnetic chip that we made was non-volatile. It was immune to any vibration and airborne contamination, and it was even immune to high radiation levels for the few potential customers that would be interested in that. What killed that technology were the advances in solid-state electronic memory with nearly infinite rewrite cycles in the late 1980s, very late 1980s and 90s. So my little company, or almost little company, the subsidiary of Intel named Intel Magnetics, was successful in announcing a working 1 megabit chip. Production readiness required a couple more years of development. The magnetic chip itself required a few support chips, all but one designed and fabricated by Intel. My primary role was to develop equipment, hardware and software to test the new magnetic chip, but I was also called on to develop design validation tests for 2 of the support chips before they were released for production. One was a current pulse generator to produce bi-level pulses, as I have indicated with my little sketch in the lower right corner. At first, the Intel test group had difficulty translating our very analog specifications into a suitable test with their test equipment. The other chip was essentially a microcontroller running various state machines. The problem was that each of the commands to this controller involved very long execution states. Again, something that was not well suited for the test vector-oriented equipment. My tests uncovered several errors requiring a few iterations of the chip before qualified for production. With the appropriate software, Not sure you can see it actually, because I think my picture is covering up the picture I put on the slide. But with appropriate software, the memory card that we manufactured and sold could be made to look like a disk with 128 kilobytes of storage. A bit more about, excuse me, about the workforce of this startup that I joined. At the time I joined, there were about 40 employees. Of those 40, there were 9 PhDs, which may sound like a very large percentage. In my group, responsible for chip design and testing, we had 3 PhDs, including myself, all trained as particle physicists. There was also an electronics engineer. We added a second one later on, and 2 technicians. The fab group had 5 PhDs with backgrounds in material science and physical chemistry. And then there were technicians and equipment operators. It was a new experience for me, learning how people with these different backgrounds approach problem solving in a very different way. I learned early on, excuse me, I learned early on that the engineers could solve electronic problems much faster than I could. But with some new type of problem, a problem without rote methodology, the physicists were often more helpful. Also, our tools were different. As one example, engineers always relied on Laplace transforms, and I'd only used Fourier transforms up until that time. In my working with Intel engineers on issues with the support chips, they came to refer to me jokingly as the white coat, meaning a scientist, because of my different ways of approaching solutions. We 3 PhDs trained as particle physicists understood the importance of statistics much better than material scientists in fab. This had important impact on our different understanding of process control. Yield improvement programs to study the effects of program changes to process parameters produce confusing results without first understanding the normal statistical variations of those process parameters. I learned later that the Intel process engineers really understood this very well. I think our people in fab lacked very much production experience. The PhDs, I think, were recently minted PhDs from their graduate program. At the time I joined Intel Magnetics, anything like a personal computer were mostly gadgets for technical geeks to experiment and play. Intel marketed a microcomputer with an 8080 processor and very rudimentary software, including a compiler for the language PLM. Their market for this microcomputer was only to be a tool for customers to develop products with Intel processors. One of my early tasks was to build an instrument to perform design verification tests for the magnetic chip and the controller interface chip. I used the 8080 based computer for the human interface of this test equipment with a serial link to the 8085 processor to exercise the chip under test. Our company had one dedicated word processor computer that was actually as big as an oversized desk for the secretaries to use. And there was a time-shared mainframe for the accounting people to use. A bit later, our accounting people discovered a software tool called VisiCalc. I don't know if any of you remember that aged piece of software, but it would run on an Apple II computer long before the Macintosh came out. Soon, Apple computers showed up on all the accountants' desks, and they loved being able to do that work right at their desk. Then IBM announced their PC with an Intel 88 processor. Immediately, all the Apple computers disappeared, leaving desks waiting for the PC availability, which took some time after the announcement. This adoption of the 8088 by IBM included a wide-ranging agreement between the two companies. One part of this agreement was access to IBM's large array of simulation tools. A very short time after I joined Intel Magnetics, well before we had working prototypes, the atmosphere changed when our target product was announced. Suddenly, there was a guard at the door 24 hours a day, checking badges on entrance and briefcases on exiting the facility. Heavy curtains permanently covered all exterior windows, not allowing any peeking in. This was quite a change from my experience in academia, so it was something I had to get used to in the commercial world. Silicon Valley has always been extremely careful about losing trade secrets, especially concerning employees leaving with trade secrets in their possession. Once we had a marketable product, that is, we could sell even engineering samples, our subsidiary was merged into Intel Corporation proper. A short time later, things were really moving quickly. Intel established a new campus away from Silicon Valley in the foothills of the Sierra Nevada mountain range in a city called Folsom. Intel claimed that Silicon Valley was too expensive, too difficult to attract new personnel. To sell the idea for employees to move to Folsom, Silicon Valley is dying became the motto of the whole move project. The magnetic operation, along with EPROMs and E²PROMs, were moved there to Folsom. They had no technical synergy, but their markets were closely tied, and markets were always the big deal with, well, not just Intel, but all the commercial companies. In spite of a very attractive offer from Intel to move there to Folsom, I decided not to leave Silicon Valley. I was concerned about the lack of other high-tech companies in the Folsom area. And in spite of claims that Folsom would become the new Silicon Valley of California, I was doubtful that that would happen very quickly. And I thought it risky to move away from the current center of high electronic technology. My search for a new job, either with Intel or outside of Intel, was my very first experience with job hunting. My offer to join Intel Magnetics, if you remember, came without any intent on my part to look for a job. This again was a learning experience. I found a job recruiter, commonly known as a headhunter, to help me. One company that showed interest made several different types of IC equipment, wafer probers, mask defect checkers, etc. My first interview was with the hiring manager, who wanted me to work on developing a network to tie together various types of instruments to a central database for their customers. At this time, turnkey networks did not exist for sale. It was create your own. He was another particle physicist turned engineer. I had listed my work developing a communication system between Intel 8080 microcomputer and the 8085 processor with a built-in serial link that I created, as well as my work as a graduate student with remote job entry terminals. He had an understanding of what I could accomplish, was very interested in me joining, and set up an interview with his vice president. The VP started the interview by telling me that I was not fit for his job, and he did not understand why his manager had wasted his time with my interview. As it turns out, and I learned, success or failure often depends as much upon the background of the person interviewing you as it does on your own background and expertise. After a brief search, I transferred to the Intel Technology Development Division into a department responsible for developing their simulation tools. Excuse me. When I joined the TD division, the 8286 was Intel's primary production microprocessor. The earlier agreement between Intel and IBM, however, required that Intel have a second source for its products, including the 8088. Advanced Micro Devices, AMD, had become their second source. It was now common knowledge that AMD was taking a large share of the 286 market. It was important for Intel to continue to advance technology to survive. It's been true for quite some time, or it was then anyway, that Intel made their money on advancing new technology and not so much on mass production work. The 8386 had been announced at this time, and engineering samples were being sold. But the unpublished news was that the 8386 yield was unacceptably low, another highly guarded trade secret. Its manufacturing costs were basically higher than the targeted selling price. There was a huge company effort to solve the yield problem before production orders could be accepted. This was viewed as a make or break issue for the company. It was a big deal. Intel's normal strategy at that time for bringing up a new microprocessor fab process or a new fab facility was to start with one of their DRAM products. This gave them a known commodity to check for yield limiters. And the DRAM fab, the fab process, was similar to that for logic circuits, unlike the non-volatile memory circuits, which had considerably different fab process. The 8386 yield was especially low at a new fab built for the 8386 compared to its yield at an existing older, lower capacity fab. A clue to where to look, possibly. There were frequent meetings, like sometimes one a day, between 8386 engineers, fab experts, and the TD department. As you might guess, and I won't go into what the yield limiter was found, the source of the low yield was eventually found, and it was corrected. And the 8386 became another success for Intel. Intel had been developing simulation tools for a long time. In addition to SPICE, they had simulation tools for many of the fabrication processes, such as ion implantation and oxide growth. They had working relationships with several universities who had developed basic algorithms to simulate these processes. Intel's group would tailor the tools to their processes and integrate the tools into their simulation system. With the IBM agreement, Intel had access to a new large set of simulation tools. It was a big job to understand how to use these tools and to integrate them into Intel's simulation system so that the process engineers and design engineers could use them. Even though that agreement had been signed a few years before my joining the TD department, this integration process was only really starting when I was working there, or when I transferred there. Intel also had contacts into universities, which they had identified as having exceptionally good engineering programs. An Intel engineer was assigned as liaison to each of those universities. The liaison would visit the campus at least twice a year, interview job candidates, possibly give a talk to students and meet with faculty. These connections also facilitated the transfer of technology tools from some institutions. I had volunteered to be the liaison with the University of California, Santa Barbara. I had not identified any faculty there who were working on simulation tools, but several of the professors were working on projects that were using Intel components, or that they wanted to use Intel components. I had a budget to donate components and design kits to these professors. I routinely recommended to faculty and also to students that master's students should complete a project thesis instead of an option of taking a few extra classes. I thought, well, I was convinced that that would be a better learning experience, and they would become more valuable to industry, especially to Intel, if that's who they wanted to work for. One of the students I strongly recommended to Intel was a very bright woman who had completed an impressive master's thesis. She was hired as what Intel called a product engineer for one of the IC departments. This was a very difficult, high-pressure position. The product engineer became responsible for a particular product, a particular IC, responsible for its quality and its its yield. If either of those suffered, it was this person's responsibility to find the solution and find it fast. I happened to see this woman sometime after she had been working at this job. She appeared very frazzled and overworked. Production work was highly technical, but it was also a very high pressure position. Likely not by coincidence, the manager of the simulation department I joined had originally been trained and worked in particle physics. There were several of us floating around in Silicon Valley at the time, I guess. He noted our similar background on my resume, which prompted him to call me for an interview. This interview was very informal. He just reviewed the work I had done as a graduate student, areas that he knew I had to work in while earning my doctorate. One missing piece of information, or one missing piece in the Intel simulation toolset at that time was statistical variation. They could not run a version of SPICE, for example, on a specific set of device parameters. Or they could run it on a specific set of device parameters. They could not, they would typically do this for so-called four corners of the process, but they could not get a picture of the distribution of circuit performance given an expected distribution of the process parameters. Similarly, they could change input parameters for the fab simulation to obtain snapshots of fab results by varying controls to fixed values for each of the simulation runs, but they could not get a distribution of process results given the level of control they had on each parameter of the equipment. My manager realized that my experimental physics background had trained me in the importance and the methodology to use statistical variation. I was asked to lead a new group to add statistical variation to all the simulation tools. My group consisted, at least my group at the time, consisted of just me and one junior engineer who had a bachelor's degree in electrical engineering. He did know more about the fabrication processes than I did. Our equipment for running simulations was an IBM 370 mainframe, which was shared with the entire technology development division and possibly other groups as well. Jobs concerning the immediate yield problem of the 386 really had loaded the queue. My knowledge of IBM job control language came in handy because I could build job decks for not only myself but other people in our TD department. One can never tell when old expertise can again become useful. My subordinate, as well as myself, were familiar with SPICE, more familiar than with the other processes. So we started looking at how we might add variations to the SPICE tool. Fortunately for us, no one expected us to provide statistical variation in time to help with the current 8386 yield crisis. It could have been very useful if it was available, but the difficulty of the project was understood by all, and our project was acknowledged to be not for the present issue, but for the long-term future. The obvious immediate way to introduce such variation is what we've all used before, that is the Monte Carlo technique. Just run the simulation many times, varying each input parameter according to some known or assumed distribution. But it was obvious to us, even when we started, that this would require too much computer time. SPICE simulation on that mainframe for any circuit that was complicated enough to be interesting would take hours. Varying the process parameters would require too much time, especially if based upon one result, we decided, or someone decided, that a different distribution of input parameters would needed to be tried. Farms and microcomputers, again, were not available at that time, but at least they were envisioned as coming in the near future. We did spend some time analyzing how our simulation could be broken into pieces allocated to separate simulations. For a possible path to be used on our existing mainframe, we looked at reducing large complex circuits into several small circuits, which could be simulated quickly. Each of these distributions of input parameters, and then apply these results to larger and larger portions of the final large circuit. It was an attempt to reduce the n squared problem down to an n problem, or an m times n problem as opposed to n squared problem. In hindsight, we should have looked at some of the fab simulators instead of SPICE to see if they ran much more quickly and could have been responsive to Monte Carlo technique. The other path should have been to learn from IBM how they approached this problem. But contact with their technical staff was tightly controlled, so we had to go through proper channels, which took quite some time. As I mentioned already, Intel had just really started getting into the wealth of IBM simulation tools at the time I joined the TD department. However, I must report that I actually was not part of the final solution of these problems. After working on these problems, basically caused by inadequate CPU speed, I was offered a job in a new startup company formed by colleagues with whom I had worked at Intel Magnetics. This new company, Magnesis, was formed to design, build, and market a bubble memory system that really looked and operated like a floppy drive, but with all the advantages of bubble memory technology. I was offered the position to be in charge of chip design, but as is true for most startups, I was needed to work on many other problems that showed up along the way. We successfully introduced our product, sold some units into markets needing storage immune to vibration or dust, and replaced a few installations of floppy disks and even cartridges that people had made of E2PROM. The cartridge at right, hopefully you can see, was sold with a drive, that is, with a box identical in size to a floppy drive, such that the cartridge could be pushed in or ejected out. A SCSI interface with software drivers made it appear as a floppy disk to both Windows and Macintosh computers. So we basically solved the customer's system integration problems, which to some extent Intel Magnetics had not gotten into. Just as production should have ramped up, solid-state disks became available and quickly took out all of our competition as well as our product. During this entire period in which I worked in Silicon Valley, only 10% of startups were deemed to have been successful. Of the two startups, of my two startups, one ran for 11 years and one for 6 years. But they were still not considered successful by any long-term measure. After my last startup, Magnesis, closed, I worked for a short time at the Stanford Linear Accelerator Center, everyone knows as SLAC, working on the control system for the accelerator. Then I was offered an experimental scientist position and later an adjunct position at the Institute for Particle Physics at the University of California, Santa Clara, my old group from graduate school year. After about 13 years working in Silicon Valley, I was able to return to my original academic pursuits, working on the superconducting super collider until its demise, and then the Large Hadron Collider in Geneva. My time in Silicon Valley was very educational. In addition to learning more about IC technologies, I learned much about project management and personnel management, topics that are not covered in most PhD programs, but extremely useful in my eventual work with large physics collaboration. So what about Silicon Valley? Even though Silicon Valley seemed big when I worked there, it is much bigger now. It is still the birthplace of new companies and new technologies. Many more are software companies now. One of Intel's claimed that Silicon Valley was dying and Folsom would become the new Silicon Valley of California. My personal opinion is that Silicon Valley continued to be attractive for high technology because of the expertise of the existing workforce. Given the economics of a startup, to start from nothing with a limited bankroll and a limited time, it has been easier to recruit needed expertise from local companies rather than to find expertise elsewhere. For those companies which are successful, moving their production elsewhere later may be still attractive, but not for the initial development process. I don't have any statistics on the success or failure rates of startups now, nor of the number of new companies starting in Silicon Valley. The business activity in Silicon Valley is still very strong. I doubt that the success rate for startups is any higher than it was unless the investors have become more discriminating. But the obvious domination of Silicon Valley's success now are large companies becoming larger, like Google and Apple, both a combination of hardware and software technology. New companies can start if someone has a clever idea, especially an idea that appears to fill a need. Creating a business plan and finding investors who believe in the plan is the next step. Advancing technology requires solutions to difficult technical problems, and it's difficult and expensive. Standard technology now is so advanced that even having a bright idea requires significant funding to test whether the improvement works or not. The basics of magnetic bubble memory technology were developed by well-funded companies like Bell Labs and IBM. My two startups did not significantly advance the technology as much as they advanced the system aspects of the technology, making it easier to use. The advances in rotating magnetic media, increases in bit density and reliability, were funded by the huge sales of such media from the 1960s to the present. The advances in IC technology and fabrication technology, especially the critical oxide layer that now provide terabytes of rewritable, non-volatile solid-state drives, was funded by the microelectronics industry and its hunger for such a solution. It wasn't just sales directly, but the sales that also enticed investors to provide funds for the expectation of future financial gains that funded the advances in these technologies that allowed this growth in already established companies. Perhaps solely investor-funded clever ideas are now more difficult to find. Sorry, I didn't mean to run off the end there, but that was the end of my
Okay.
Okay. That was kind of an abrupt end. I wasn't keeping track of the slides and ran off the
No problem. That's fine. Thank you very much, Alex. That's very interesting, and that's great that you put there some lessons to be learned. That's a very good thing. So I guess we can open the floor now for questions. In fact, while more questions are coming in, I have a couple of questions, especially from what you mentioned. Some things that not that surprised me, but caught my attention is that one is that you put some stress and commented the relationships of the companies and the startup companies and also the big companies with the university, and there were a lot of PhDs and even people coming from more theoretical areas like particle physics and so forth. So do you think that there was like an academic atmosphere there in Silicon Valley and in these companies, maybe more than a purely industrial one? And do you think this might be one of the keys for this success?
There was certainly interest in academia to provide solutions or ideas for technology advancements. The atmosphere at the company, though, was quite a bit different than academia. I mean, I mentioned, for example, the emphasis on secrecy. You know, you had to
Yeah,
have
I wanted to ask you about that too. Yeah,
you had to have a badge to get in, and I mean, once the guards knew you, they were not really strict about, you know, checking your briefcase on the way out. That didn't happen very often. But if you were a relatively new employee, or there was a new guard that hadn't seen you around or whatever before, it was accepted that they had the right to look in your briefcase or whatever it was you were carrying out. When I left Intel to join the second startup, I carried a small box full of, you know, desk stuff and whatever. Well, they looked through that whole box before I could walk out the door.
wow.
So that was part of the different environment. But the other day-to-day difference was the tension and stress to get things done in a timely fashion. I always commented on the fact that when we ran into problems in our research programs at the university, unless it was really some strange emergency that we solved it immediately. We were really interested in what's causing the problem and what's the solution. And at Intel, or especially at the startups, there wasn't time for that. As soon as something worked, you just went on, and you didn't worry about what had caused the problem. And it may come back later, but when it comes back later, we'll deal with it then, because we don't have time to deal with it now and dig into what was really the underlying problem. So that, I think, was a big difference, how you approach problem solving. Now, that was true for these commercial companies. IBM, for example, has a huge research division. And that really, and I have some knowledge of it because that person that hired me, that had worked at HP and then left to form Intel Magnetics, at some point, he left Intel Magnetics and he got a job in the IBM research division. And so we had many meetings where we chatted about what he was working on and how that was. And there, the emphasis again was digging into solving, not just solving the problem, but finding out what the underlying cause of the problem was. So I think big companies that are big enough to have a real research division, those divisions themselves are much more like an academic environment than a commercial company.
But regarding the people working at the companies, there was a high percentage of PSD, for instance, right?
Yes.
Okay.
But I guess you might say we had to adjust our thinking and our attitudes about how we solve problems and how deeply we get into solving the problem.
I understand. I see.
At one point when I was working at Intel Magnetics, well, one of the characteristics of this magnetic bubble memory technology was that the chip itself, after fabrication, would have a few defects. None of the chips we could make were completely defect-free. And so we had developed a method for masking out defective cells and working around them. And how we found the cells and whatever. And so my friend and I, my colleague at Intel Magnetics and I, wrote a paper about that whole issue, because in DRAMs, for example, people were talking about having ways of masking out bad cells. This was, again, back in the early 1980s, but I don't think anybody was employing that in the DRAM chip at the time, but they were thinking about, well, how would we do that? And so there was some interest in what we were doing, just from a sort of philosophical way of, yes, this really is becoming important even for electronic circuits or whatever. But we basically had to work on that paper in our spare time, because Intel Magnetics wasn't interested in the fact that we had some good ideas about this and wanted to write a paper about it. They were interested, oh, it's good that you've worked this out because we're making use of that, but don't bother me with an academic paper that you're going to present at some conference. So again, that's a different culture, a different attitude about what you're working on.
I see. I got a couple of questions from the chat. Let me see. One is, what is your opinion regarding the advancement of quantum technologies and the interest of this area in Silicon Valley?
Unfortunately, I have no information about the interest in Silicon Valley, because I really have not been involved in or monitoring Silicon Valley work for quite some time. As far as how useful it could be, I'm sort of having a similar experience with these quantum devices as some other physicists have had when they get to be a certain age. I remember I went to SLAC to hear a talk by Feynman, because he had promised a year before that he was going to study QCD, and because he didn't understand it, but he was going to spend the whole year trying to understand it with one of its experts. And this was going to be a talk about what he learned about QCD. So he stood up.
The audience might need an explanation of the acronym.
Well, oh, I'm sorry. Quantum chromodynamics. It was.
Thank you.
It was a way, or it still is. It's an extension of QED, quantum electrodynamics, to the strong force that holds quarks together in protons and neutrons and whatever. Anyway, one of the other physicists at SLAC gave him a very nice introduction. Feynman stood up and he said, I really worked hard on this the entire year, and I still don't understand QCD. And I can't report on anything because I still don't understand it. And he sat down. That was the end of his talk. But anyway, what I'm pointing out is that sometimes younger minds are better than older minds at picking up stuff and understanding it. And I'm having a similar problem with these quantum devices, is that I haven't spent much time looking at it, but it still seems contradictory that something that you can apply Heisenberg's uncertainty principle to something that you want a definite answer to. So I'm sort of claiming old age, I guess, as a reason for not understanding that. So.
Okay. Another question that we have very various questions that are very different from each other. The one is, just for curiosity, is Folsom a tech hub of any sort today? Folsom?
Is Folsom what?
A tech hub of any technological hub of any sort today? Is there any technological companies or movement there, or did Folsom completely became out of technological companies or anything?
As far, again, I apologize for not keeping track of a lot of this stuff, but as far as I know, the Intel campus is still there. And there were some aerospace companies in the Folsom area that were relatively high tech or whatever. And this was back in 1985, 86 or whatever. But I don't know if there were a lot of other high tech companies that moved up there or joined that area. I certainly, you don't hear it in the newspapers or whatever about big things happening in Folsom. So it certainly has not become the Silicon Valley of California. That's for sure. But there are still a few companies up there. Yeah.
Mm-hmm. Another question that we have is, despite microelectronics is now a big rolling machine, everybody is talking about the talent shortage. Was there was there such a shortage as well in your time in Silicon Valley when things started moving?
Yeah, I think there was enough of a shortage to mean that recruiting personnel was a big deal. And for example, the reason Intel had all these connections with universities that were identified with good engineering programs is because they needed help in recruiting. And so my going to Santa Barbara, UC Santa Barbara, was part of the personnel recruiting program at Intel, and they had a large number of universities had similar connections with Intel. And again, that was also the reason why I think the workforce and personnel, the workforce in Silicon Valley was one of the reasons why Silicon Valley didn't move or didn't get dispersed off to other places, because a startup company would typically look for stealing employees away from other companies in Silicon Valley first, and then they look for new hires out of universities and whatever. And that was just a measure of the limited personnel base that they had to work from. And now I think, even though it's even though there are a lot more universities focused on high tech, on what do they call it, STEM programs, so there are a lot more people coming out with appropriate degrees. There's a lot more companies looking for people, so I'm guessing that the shortage is still there. It's unfortunate, along with all of that the cost of education in the United States is so high, because it warps how students design their course load. When I was at UC Santa Cruz, I would be advisor for undergraduates. And when I look over their courses, these were physics students, but they would have some extra math courses or whatever that weren't required. And they had very little in the way of non-technical electives in their course load. And I questioned, well, why are you doing that? Well, if I have these two other math class courses, I can have a double major in physics and math. And I asked them, well, what do you think that's going to buy you? Oh, it'll be easier to get a job. And I suggested it probably won't be any easier to get a job. And you're really losing an opportunity to take up some other interesting areas, So I'd suggest, well, why don't you take a philosophy class or an art history class or something like that? No, they stick with their extra math class. And it was all predicated on the fact that they needed what was really in the back of their mind was this big student loan that they had taken out over the course of their 4 years that they had to pay off when they left. And they wanted the best opportunity to get the most high-paying job to pay off these loans. And I think it's a very sad situation for our American undergraduates to be in. But I'll get off of my soapbox.
Oh no, it's interesting. Looks like we don't yet have this problem here.
Oh, that's good. Right.
There's another question. Was it easier back then for a startup to have access to the necessary resources to design and manufacture custom chips for their products that it seems to be today with most advanced nodes?
Fortunately, there are programs in the United States like Moses that you're familiar with. We used to make use of that quite a bit, and they actually well, they probably don't have the cutting edge process available, but they have some very advanced processes. And so, in fact, Moses a few years ago shifted their whole cost methodology and whatever, and so they're really more targeting startup companies than they are universities. So one can get maybe the top leading edge process available, but you can get one or two steps down from that to work on through things like Moses. And Europe has similar programs. So if you're developing something that requires a process being developed, then it's more complicated. Then you have to have access to a fab to be able to do that, along with the proper engineering staff that knows how to do that or what to do with the fab process. But so that was always difficult. I mean, one of the problems we had with both of my magnetic bubble memory startups was that we needed a fab that was completely divorced of electronics fab, because some of the metals that we were using, the magnetic metals, were considered to be disastrous for most of the electronic fab processes. So in both cases, we needed to have access to our own, private fab facility, which was difficult to put together. And that would be true also, I think, if your great idea for improving the electronic device, it requires some novel way of fabricating them. You probably wouldn't need a fab that's completely independent of other commercial fabs, but you need to have access to the fab by your people, so your people could go in and turn the knobs and run the process as they wanted to test their new idea.
I see. I also had a question out of curiosity, because you mentioned the subject of security, and so this was more like a paranoia coming from the so much money involved in some of these companies, or it was a real problem for these companies? Was it actually happening? Did you witness any of these things, like people going out and stealing ideas to other companies and things like that? Or was it not really based on real things going on? Because you mentioned the scrutiny of your personal belongings, and also the shades in the windows. This is really, I was surprised about that.
Yeah, the building that Intel Magnetics moved into in the beginning had fairly large windows around the entire perimeter of the building. And so with these windows, if you were standing outside on the sidewalk or whatever, you could look in and see what we were working on. It's difficult to imagine that you could see something small enough to actually be of use to you, but you certainly could see, well, these guys are testing chips because I can see chips running through, or something like that. So you could tell something about the progress that the company was making. I think the bigger issue that they've been concerned about are employees leaving to start their own company or to join another new company and bringing, sort of trade secrets from the first company to the second company. And so you do have to be careful when you leave one company and join another especially if the company you're joining has visions of working on the same type of product as the first company. The first company is going to want to know a lot about, well, what did you bring with you? And in most cases, it comes down to, if what you're bringing is in your head, there's not much you can do about it. But if you're bringing pieces of paper that describe, say, the fab process or something or other, then that's something that they could clamp down on. They could sue you for stealing trade secrets. But what's in your head, well, as long as your head's clear enough to remember, you're probably okay. At least that's the advice that I was given by a few lawyers that I talked to along the way.
Okay, so I think we don't have more questions, and I will hand it over to Sabela. But before that, I want to thank you again very much, Alex. It's very nice that you made this talk with some lessons to be learned from that period. I think that is very, very interesting, and thank you again.
You're welcome. Thank you.
Thank you very much, Miguel, for proposing the talk, and Alex for accepting the invitation and for being clear and transparent about your time in Silicon Valley. I hope everybody enjoyed it. There were some comments in the chat saying congratulations and thanking you for the talk.
Oh.
So thank you again, and we will turn off the broadcast now. There are more talks about the transistor to enjoy in our YouTube channel, so I invite you to see them if you haven't yet. Thank you very much, and have a good afternoon, morning for you, Alex, once again.
Very good. I enjoyed working on the project, so thank you.
Thank you.
Thank you. Goodbye.
Bye-bye.